Once again, greetings from IIT Kharagpur. I hope the first two lectures in this course, Physics of Nanomaterials, have given you an overview about what are nanomaterials and why the field of nanotechnology is growing so rapidly. These two lectures must have also given you an overview to realize the fact that we are surrounded by nanomaterials. And now, in today's lecture, let us continue our discussion in this direction and tell you why this field of nanotechnology is becoming so important in today's world and what is the need of having such new nanomaterials. So, in today's lecture, we will give you an idea about the need of nanomaterials. We will give you some basic and very important applications. We will extend our discussion and understand further the importance of the term surface to volume ratio, and you will see that as we go down the size, that means we reduce the size of the particles, then we have to talk about the quantum effects in these materials. What are those? We will give you a brief introduction to it, and you will very soon see a detailed discussion about the quantum effects in nanomaterials in subsequent lectures. And if you see the type of nanomaterials which we will be talking about, why they are becoming important? They are becoming important because their properties are very different, and those would also be discussed in the latter part of today's lecture. So, what have we discussed till today? We have seen that if there is a bulk material with x, y and z direction growth. So, you have a 3-dimensional bulk material. So, if you start reducing from one side, so what will happen? So, if you start, let us say, cutting the material layer by layer from the z direction. So, what do you get? You are reducing the size, you get a plane like structure. In the next slide, you will see that these are called as quantum well. Then we will extend that. So, we have in the first step we have reduced the size from one dimension, and now let us reduce the size from the second dimension also. So, let us start reducing the size from another dimension while leaving the third dimension in an extended region. So, what will you get? You will get such kind of structures. These are real structures with atomic arrangements in a given order. Now, what is the third? The third is that you start also reducing the size from the third dimension. So, first step was cutting from one, then we had cut the second, and then now we are also cutting from the third dimension. So, what do you get? You actually get a confined system. So, all the three dimensions are now in the range of 1 to 100 nanometers. So, if you plot it, this is bulk, the second structure is called as quantum well, then you have reduction from two sides, you have quantum wire, and then if you have the reduction in size from all the sides, then it is called as quantum dot. So, typically if you see cube type particle and then how it will move as we go from well to wire to dot like structure. Similarly, if you see bulk spherical particle, the quantum well of spherical particle would look like this, the wire would look like this, and then you have a dot looking like this. So, this is the thing which we are talking about: quantum well, quantum wire, quantum dot. We had talked about confinement effects, and we said in the previous lecture that electron will get confined. Let us see what we meant in this direction. So, let us say there is an electron. If you see, the electron in a bulk is able to traverse long distances in all the three dimensions. But if you see a quantum well, then in this direction it is confined, whereas in this direction it can traverse a long distance, and so well in this direction. So, it has confinement in one dimension. Now, if you see a wire structure, it has confinement in this direction as well as in this direction, but it can move freely to long distances in the third direction. So, there is a confinement in two directions, whereas in quantum dot you have confinement in all the three directions. So, now you understand what we meant by confinement effects. That means how the charge is moving in these systems. Obviously, if you can restrict the charge movements, then their properties would be different from one structure to the other, because the first thing that you will see is the motion of, let us say, electron is getting restricted. Then what is the corresponding property which will get impacted? The conductivity, that is the electrical conductivity will get modified, and you may see anisotropic properties in the three dimensions. So, you can go from isotropic properties to anisotropic properties, or you can tailor the conductivity as per as your requirement by choosing the right dimensions of the particle. So, just by looking at this figure, you can clearly see that the electrical properties of the systems would be different as we move from well to wire to dot with reference to the bulk particle of the same molecular formula material. So, if we put these facts which we said in words, the properties of the nanomaterials are expected to change as we move from one type of structure to the other. Why are we emphasizing properties every time? The word properties, properties, properties. The reason is because the physical, chemical, electrical or mechanical, even optical properties decide the usefulness of a given material. So, if you can tune the properties of these materials, that means you are opening new avenues for the application of these materials. Hence, what are the properties which will get modified as we move from one type of nanomaterial to the other? Clearly, mechanical property, thermal property, melting, electrical, magnetic property, catalytic property, diffusion or diffusivity, optical property, electrochemical properties, and so on so forth. These are some of the properties which will get modified, and you can list many more. This is not an exhaustive list which is mentioned here. There are many other properties which are being discovered on daily basis that are modified as we move from bulk to nano-sized particles. Mostly it is said that it is the surface to volume ratio of these nanomaterials which drive the property modulation. What do we mean by surface to volume ratio? This means that when you reduce the size of the particles, then more number of atoms are located near the surface of the particle, on or near the surface of the particle, because the volume has been reduced, but the surface is quite large. Therefore, the atoms are near by the surface of the particle, and therefore, each atom can contribute to the physical, chemical, mechanical or other properties of that particular molecular unit. Hence, just by going back to our school knowledge, where we understood that catalysis is driven by the reaction of the catalytic particles with something. That means, if you have more number of atoms which is driving a chemical reaction, then what is the basic need? Suppose you have a large particle, then most of the atoms are inside, but the reactions will only take place at the surface. So, you actually have a large particle, but most of the weight is being lost. So, you are not utilizing the available atoms because they are not at the surface, they are in the bulk, and the atoms are not exposed for carrying out or driving any chemical reactions. But if more number of atoms come on the surface or nearby the surface, then they can start contributing to the chemical reactions. So, what do you expect? Immediately the reactivity, and if I talk about in particular catalysis, then the catalytic efficiencies of these nanoparticles would be much higher. And that is why you will find a major application of these nanomaterials are coming in these kind of applications. For example, if you talk about platinum nanoparticles, these are extensively used in fuel cells. I just took this example of fuel cells because after solar cells, batteries, supercapacitors, fuel cell is another technology which is seeing significant revival and renewed interest as we go for off-grid applications or some dedicated applications where large amount of energy is required, but it is not connected to grid. So, fuel cells is going to be a major technology in coming decade or so. In biomedical, nanoparticles with large surface areas can actually efficiently carry and release drugs at targeted site. What is called as targeted drug deliveries, or sometimes these kind of systems are called as nanobots. So, we have small sized nanoparticles on which these structures are coated, and then as they move along, then they have the capacity to link with the site where the virus or the bacteria is there and specifically release these drugs at that site. So, they have a large application, and I would suggest that just think before you start reading examples from book directly. Please think and make a list of applications where you think that the role of surface to volume ratio would be immense, and that would make nanoparticles very useful for today's mankind. Why is the property, or why are the properties of these nanoparticles or nanomaterials so different? It is primarily because at nanoscale the quantum mechanical effects become very prominent, and that drives the change in the response characteristics when compared with the bulk materials. Quantum mechanical picture we will discuss in next few lectures in detail, but we all know from our school days that quantum mechanical confinement drives the formation of discrete energy levels rather than continuous bands, and this phenomena modulates the electrical, optical, magnetic and other properties. So, immediately you can see that you may have a material. When it is in bulk size, let us say it is an insulator. You start reducing the dimensions of that particle, and when the system goes to a condition where discrete energy levels start taking over, maybe you may see a transformation from insulator to semiconductor or insulator to metallic or vice versa. Initially the material was metallic in nature, and then it is going to insulator. So, it is called as metal to insulator transitions. Mostly if you see from thermodynamics, we have been believing that phase transitions are driven by two parameters, either temperature or pressure. This is what we have been understanding, that you change the pressure, the phase will change. You change the temperature, the phase will change. But here at the same temperature, at the same pressure, you change the size of the particles and the particles may undergo a phase transition, and this is called particle size induced phase transitions. It is a very interesting phenomena, because if you do not have to change the temperature of pressure, then you are actually saving lot of electricity, lot of additional equipments, and you have a simpler way to introduce phase transitions. So, very interesting. Similarly, you can see that the semiconducting properties of let us say CDSE quantum dots can be tuned, and the associated photoluminescence of these particles can be very different. Have we seen this example earlier? Can you get an idea? Yes, similar things were being talked about when we were talking about the nanoparticles of silver. You go from 40 nanometers to 80 nanometers to 100 nanometers, you can go from one color to the other, and then that can be coated on a piece of glass and you can see different colored glasses. But now we are understanding the reasons why these things are happening. Similarly, you can introduce super paramagnetism in magnetic nanoparticles. They can be used for magnetic data storage, medical applications, transformer oils, which are huge applications. Or you can also get quantum effects in other semiconducting properties of nanomaterials, and you will get these particles which can become useful for displays, let us say solar cells, imaging and many more. So, just by tuning the size, what are we getting? We are getting different applications of these nanomaterials, and that is the need of nanomaterials. These are all high end applications which we think of today. High end on one side, but routinely available around us. Few decades back, we may have said, okay, solar cells are available at certain places, but now if you look around, you will find the usage of solar cells everywhere, for street lights, to small toys, to mobile chargers, to grid level production of electricity. So, at one end, the physics behind the development of nanoparticles which actually drive the photovoltaic effects is significantly different from those observed in bulk particles, but the application is huge, and that is where nanotechnology is entering our lives on daily basis. If you see the various types of ICs, integrated circuits, you have LSI, MSI, VLSI, before that LSI, ULSI. What do we mean by this? This means you have, if SSI is used, then SSI means you have small scale integration, meaning that you have 1 to 12 components on a given chip. From there you go to MSI, medium scale integration. You can go from 12 to 100 or maybe few hundreds. Then you have LSI in the same dimension. I am not changing the size of the wafer on which the circuit is being grown. That means I have the transistors, I have the diodes, I have the resistors which are being constructed on the same chip. LSI few hundreds to few thousands, VLSI few thousands to tens of thousands or maybe up to 100,000. VLSI you have even higher. And then ULSI, you have few hundred thousands to millions of components being constructed on the same chip. How is that possible? We went from 12 components to, let us say, 1 lakh components on the same wafer. Obviously, if you have so many components on the same wafer, then what is happening? You are getting improved functionalities. You are getting huge amount of applications which can be obtained from these integrated circuits, the chips which we are talking about. And if you have so many components, then what is happening? Immediately you are miniaturizing the size of the device. So, you can introduce lot of applications without increasing the size of the final device. And this was actually very nicely explained, for example, in transistors. If you see the Moore's law, it says that approximately the number of transistors on a microchip, it doubles in nearly 2 years, every 2 years, though the cost of the computers is halved. Now, this was observed by Gordon Moore. This led to exponential growth of computing power, miniaturization and performance per cost. You have seen it yourself. Just compare the computing powers of your desktops which were there maybe around 10 years back. The same kind of computing power is now available in your mobile phones. You can type, you can do some processing, you can do mathematical calculations, you can do writing, you can take pictures in the same small mobile phone which was being done using a large CPU connected to your screen in the desktop computers. So, you went from desktop computers to laptops, and now similar capacities of computing is coming into your mobile phones, the smartphones. Why? Because you are now getting this capacity to integrate so many components in a small size chip that can give you such high functionalities. And that is where the importance of nanotechnology is being transferred to nearly everybody in and around us in one way or the other. Nowadays, there is a technique called lithography, using which you can easily construct patterned structures which have dimensions of the range of 2 nanometers or so. And then just imagine how many components you can construct if you have a 1 square inch wafer, if one structure is equivalent to one component. Huge amount of components can be constructed. This is what the thing which I was talking about. This is the first transistor which was constructed. And now what we are talking about? The IBM's first transistor which was reported is approximately 2 nanometers or so. So, what will happen? Obviously, you have gone from here to here, and if you see, let us say this is maybe 100 centimeter square area. Now, in this area, if you have to make 2 nanometer size components and then you can distribute it in this whole 100 centimeter square area, just imagine the power which can be obtained from such a computer. And that is where new terms and new devices are coming into the vocabulary of today's science and technology. For example, nano electromechanical systems, NEMS. They are utilizing nanomaterials to create highly sensitive sensors, again driven by the much smaller sized particles. Generally, we sometimes believe that miniaturization can lead to loss of power, the capacity to perform certain activities or the number of activities which can be performed if the size of a particular electronic device is reduced. More is the functionality, you must increase the size. But nanotechnology tells us no, what we can do? Even if you reduce the size, you will get the opportunity to increase the functionality by many folds. So, you can reduce the size without compromising on the functionality. In reality, you can add many more functionalities, making such devices portable. Means there are advantages that you can have smaller devices which are lightweight and compact. The major disadvantage associated with this fact is that to make very small size ICs, you need specialized labs and trained personnels to make and fabricate such ICs or the devices. So, you have to have capabilities to handle and manipulate the properties at nanoscale. But now this fact is also very easily addressed. You will see as we go along, it is not a difficult task anymore. If you understand the chemistry of these nanomaterials, you can make large number of nanomaterials. If you understand some of the fabrication techniques, for example lithography, it is not a difficult technique to expertise. Yes, but you have to have the knowledge and expertise. Similarly, you can tune the performance, you miniaturize these devices, what will happen? You will have lower power usage, but because of quantum tunneling features which may come into picture, there is a possibility of leakage current. So, it is not true that as we go on reducing the size, everything is advantageous. There would be limiting factors which will come into the forefront, and at each point you will have to address this limiting factor before going to the next step. You can reduce the material usage. As we have seen, you can add new functionalities, but sometimes the properties may change if there is variation in particle size, even slightest of particle size. Then the reproducibility of these fabrication processes have to be carefully controlled, otherwise modulation in the quantum effects will result in slightly different properties from one batch of material to the other. You have economic impacts. Although there is huge gain because you are getting new consumer electronics, wearables, you have medical devices, Internet of Things based devices which will earn you revenues. But before you do that, you also have to do lot of research and development and invest in the manufacturing of these devices. So, the initial cost, that is the capital cost, can be quite high, and then the running cost is also going to be significantly high. Why? Because these will require trained people like you who have knowledge in this area, and knowledge is not cheap. If I am trained, you will expect that you get proper remuneration for that, and having skilled and trained scientists who can run these R&D labs will require continuous investment. But you can have various applications, as we saw. To an extent, sustainable, and the term sustainability is sometimes associated with nanoparticles and nanotechnologies. Although they reduce e-waste by efficient design and biodegradable nanomaterial usage, the recycling and disposal strategies of nanomaterials can be challenging. How do you dispose of these nanomaterials? Because they are so light, even if you try to sediment and in a water, they are actually suspending on top of it. So, how do you take them out from a suspension? Generally, how do we take impurities out of a suspension? You make a solution out of it, let the impurities settle down and decant. You have the impurities at the bottom. But here the nanoparticles being so light, they are hanging or they are suspended on the top of the water layer. And as we discussed, there are manufacturing challenges. Let us see why these mechanical properties, for example, can change. The Hall patch effect tells that as the grain size decreases to nanoscale, the number of grain boundaries increase. So, you have one grain, you have the other grain, then these are the boundaries. So, obviously, what is happening if you have a polycrystalline material and you have reduced the size? These grain boundaries block the dislocation motion, because if you have a boundary and there is a crack moving, the crack sees a boundary and it cannot traverse to the next particle, and hence this is a example which you see. If you see the flooring where you were using various kind of mosaics in earlier times, before these ceramic tiles have become very popular, or even in ceramic tiles, you will see that there is a gap between two consecutive tiles, or when we were doing the mosaic based flooring, there was a glass sheet between two areas. Why? For example, if there is a crack which travels through one of the tiles or the mosaic area, then when it hits the boundary, it cannot straight away transfer on the next side, and therefore, the damage is actually restricted. So, that is what the advantage is. The number of grain boundaries increases, and this blocks the dislocation motion. And the relation gives between, let us say, phi y is equal to phi I plus k d raised to the power of half, where phi Y is the yield strength, phi I is the frictional stress, K is the strengthening coefficient and D is the grain size. If you plot this curve, then you can clearly see that there is a maximum attainable yield strength. Below a certain region, you will have reduced strength, and above this critical point you will have a reduced stress because of this relation. So, you can immediately find out for a given material what would be the critical grain size to obtain the maximum sustainable yield strength. This is another example where systems, for example, nanoscale diamond needles or nano diamond or TIN nanoparticles, they show extreme hardness. So, these are grown, and you can see when you take the pictures, the corresponding SEM pictures, they show extreme hardness. As we have discussed that when you change the confinement from one side to the other and to the third, the electrical properties change. So, if you just see the conductivity, you go from one material to the other, then just by changing the size of the particle, the nature of the arrangement of atoms, these are all carbon based systems. It is only how you are arranging the carbon and what are you talking about. Are you talking about a tubular morphology, that is carbon nanotube, or you are talking about planar morphology, the graphene, or you are talking about the Buckminster fullerene, which is more like a football like spherical arrangement of carbons. Just going from one arrangement to the other, you can change the conductivity of these structures. The same thing is then obtained for optical properties. This is primarily driven by localized surface plasmon resonance and quantum confinement effects appearing together, and therefore, the localized field which you have, that results in different forms of oscillations, and that modulates the optical properties which you observe. And you can get different types of silver ore, and we have already seen that when you change the size of, let us say, gold nanoparticles or silver nanoparticles, the colors which you get are different. You can also change the shape of these nanoparticles and you will get different forms of emissions coming out of these nanoparticles. What we saw in the first two slides, that if you are having gold nanoparticles in the range of 10 to 20 nanometers, let us say spherical particles, then you have red, 2 to 5 nanometers you have yellow, and more than 20 nanometers then a purple color coming out. In comparison, if you take silver nanoparticles, 40 nanometer particles blue emission, 100 nanometer particles yellow emission, prism shaped particles giving us red emission. Now, there is a very interesting phenomena which has led to the development of new area which is called as magnetism at nanoscale or nanomagnetism. When you reduce the size of the magnetic particles, their properties are entirely different from those which are observed in magnetic nanoparticles. And for example, if you take a particle which is ferromagnetic in nature and then you reduce its size, you can actually go from a ferromagnetic state to a superparamagnetic state. And this is happening because of the formation of elongated grains in nano size particles, and this drives this transformation. We will discuss this in detail when we dedicate 3 or 4 lectures to this field, that is magnetism at nanoscale, and hence you can get newer properties and newer applications for a given magnetic system. So, what is superparamagnetism? Just by looking at the hysteresis loop, you can see ferromagnetism is a loop which is having large area. Paramagnetism is no loop, but superparamagnetism has nearly no opening of the loop, but it has much higher saturation magnetization, and then this can be used for various applications. So, superparamagnetism and superparamagnetic material and their development has become a very interesting field for various applications. For examples, they can be used for medical imaging or scanning of certain parts using a suspended particle. These can act as contrast. Most of the things which we talked about were given, most of the things we talked about today are given in these 2 references. You can read them from these 2 books. Let me summarize. So, what we have seen, that in continuation to the first 2 lectures where we gave an introduction to the field of nanomaterials and nanotechnology, today we have talked about the need and the application areas where these nanomaterials are being utilized. The role of surface area to volume ratio, why it is so important, and what is the driving force behind the property modulation in nanomaterials. It is primarily the quantum mechanical effects, which we will discuss in coming lectures in detail. So, thank you very much for attending today's lecture.